Good morning. There is a little bit that I want to explain more about the Navier-Stokes equations before getting into the specific topics, which is the use of fraction step schemes for the time integration. This is not directly related to the stabilization using the variational multiscale framework, but I think any, let's say, course on finite element methods for Navier-Stokes equations has to contain a little incursion into these schemes. So what are fractional step methods for the time integration? Essentially, they are schemes to integrate in time the equations that the objective of which is to uncouple the calculation of the velocity and the pressure. Okay. The coupled calculation of velocity and pressure is what we call monolithic schemes. No? So this is in contrast to monolithic schemes. We have fractional step schemes. So I will go just to give the idea, and also some of the ideas that will appear here will be recovered later in the stabilization methods. So I will first talk about classical projection methods, then second order methods for the continuous problem, and then an algebraic approach, which I think is the most powerful. What is the origin of splitting methods, also called the splitting methods or fractional step methods? Well, in classical so-called projection methods, the starting point is Helmholtz decomposition, sometimes also called Hodge decomposition, which we saw already in the context of the Stokes problem. It's the same that we saw before. Okay, given a vector field, it can be uniquely decomposed into a solenoidal part and a potential part, the gradient of a function. Okay, we know that. And now this taking the solenoidal part of W or taking the potential, the gradient part of W, can be understood as projections, because if we have a vector that is already solenoidal, that the composition gives the same vector, of course. So those are projections. P squared is equal to P. Therefore, we can decompose W into the projection onto the divergence-free vectors plus the projection onto the gradient vectors, the potential vectors. Okay, so we have the decomposition of any vector into the solenoidal part plus the potential part. Okay, so let's look at the Navier-Stokes equations. Those are the Navier-Stokes equations, right? The only thing I have done here is I've moved the convective term and the viscous term to the right-hand side. So we move that to the right-hand side. And on the other hand, if we assume enough regularity so that the spatial and temporal derivatives commute, so Schwarz's theorem applies, then we have that this term, this one, is divergence-free. Okay? Therefore, we have a vector, which is this one vector, which is f plus nu Laplacian of u minus u gradient of u. This is one vector that is split into a gradient plus a divergence-free field. Okay, one vector that is split into a gradient plus a divergence-free field. Therefore, we can see that that component is precisely the projection onto the space of divergence-free vectors of the right-hand side. Okay, that is a simple idea. But we can write the Navier-Stokes equations in this way. du dt is the projection onto the solenoidal space of vectors of this vector. That is the idea of the method developed simultaneously by Jorin should be pronounced, I was told, Jorin and Temam. He was Paul, and Paul told me that he should be pronounced Jorin. Okay, so now what is the idea? What is the idea of fractional step methods, or those original so-called projection methods? The original name was projection method because of this. The idea is, okay, if I have to find u such that du dt is the projection of a vector, I'll do the following. A vector that depends on u, I'll do the following. First, I will skip that projection. I will split that projection. I will solve this equation, and then I will project. Okay? So that will not be my solution, but then I will project. Okay? So that's the idea. As simple as that. And that will give me, hopefully, a good approximation for the final solution. Good. And by the way, when I project, what does that mean? projection means that I have to solve this problem. The projected vector is going to be the original vector is going to be the projected vector plus a potential. So that is what is said here. The original vector is going to be the divergence-free part plus the potential. You see, plus the potential. Okay, so that is fine. That is good. However, at the numerical level, there will be an error due to the uncoupling of the steps. Why? Because these steps are in principle coupled, so we should solve at once. In fact, there is I should have put maybe here u without tilde. This is what is done in practice. So if I put here u without tilde, that would be exact. So I compute that vector, which is not the projection, and then I project it. But what is the problem if I put here u without tilde? If I put u without tilde, the problem is that I cannot solve that problem alone. So I should solve the problem in a coupled way. You understand? So at the numerical level, when we implement exactly what he said here, there will be an error due to the uncoupling of the two steps. Okay? And in fact, there are two possibilities. One is to treat u tilde as an independent variable and to track u tilde everywhere. And the other, which is the most used one, is to apply the previous decomposition on each time step. What do I mean by that? I mean by that the following. So remember, we have the equations, which are the temporal derivative of u plus u gradient of u minus nu Laplacian of u plus gradient of p equals to f. Then we compute temporal derivative of u tilde plus u dot gradient of u minus nu Laplacian of u equals to f, and then the du tilde du equal to the projection onto the divergence-free space of the tu. Okay, that is what would be exact. Okay, that is what would be exact because of what we have said. So the solenoidal part of f minus this term would be precisely this, and that would be the potential part, which would be recovered in the second step. However, there will be an error because of the splitting of these two steps when I put here u tilde. Okay, when I put here u tilde. And now that I have this, I have two options. Imagine we use, and that is equivalent to say, by the way, to that the temporal derivative of u plus the gradient of a certain function phi is going to be the temporal derivative of u tilde with the condition that the divergence of u, or the temporal derivative of u, is equal to 0. Okay? That's what I have said. Good. So now we would have two options. One option would be to, let's say, discretize this in time. Suppose we use, for example, the backward Euler method. We use the backward Euler method, and we solve these equations, right? Excuse me, there is no gradient here, equal to f. And then the other equation, un plus 1 minus un divided by delta t plus gradient of phi equals to u tilde n plus 1 minus un divided by delta t with the divergence of un plus 1 equal to 0. Okay, so this is a possibility. You see, this is a possibility. This is interesting because what is the advantage of this? The advantage of this is that allows us to uncouple the calculation of the velocity and the pressure. We will see that a little bit more. But from here I can compute u tilde, and from here I can compute u. Okay. And there are two options. This is one, to keep u tilde as an independent variable. Okay. But there is another option, which is what is used in practice, which is to do that splitting at each time step. So in fact, one uses the exact velocity, the velocity that is divergence-free from the previous step. Okay? One uses the velocity that is divergence-free from the previous step. As you see, this term cancels with this, and then this one can be moved to the right-hand side. But we will see later. Anyway, there are these two possibilities. That is what I said here. The usual one is to take u tilde as an intermediate variable and just forget it. Once you have computed it, forget it, and just keep the the variable un. So this is the scheme. This is exactly what I wrote there. This is the scheme. So 1 over delta t, u tilde n minus un, so this is the temporal derivative of u tilde, equals to this term. And then the projection step, which is this one, the projection step, you see, in this case, as I said, that's what I have said there. This term and this term cancel, so this term and this term cancel, so this cancels. I can move this to the left-hand side, and I have this equation. Okay, and that's what is repeated here. That is repeated here. Okay, and clearly I say the variable phi that in principle is just introduced as the variable that appears in the Helmholtz decomposition or Hodge composition. The variable phi can be understood as the pressure. So that's the problem I will finally solve. Okay, this is the problem I will finally solve. As you see, from the first equation, which is a convection diffusion equation in time, I solve for u tilde, and then from the second equation I can compute the pressure and the end of a step velocity. The second equation is still coupled, you see, that's still coupled. We have to solve for the velocity and the pressure at the same time. So it's still coupled, so we have to solve velocity and pressure, but it's very easy to uncouple. Well, it's very easy to uncouple. How do we uncouple that? If we take the divergence of this equation, the divergence of u tilde of u is 0. So, and u tilde is already known. So we solve for the Laplacian of P, and then compute the pressure, and then we move to that equation again and compute the velocity. We will see that. Okay, so that is the scheme. So estimates. How do we prove that the method is stable and convergent? First of all, we have to introduce the discrete counterpart of the spaces that I introduced yesterday, if you remember. I introduced the following spaces. LP in time of functions that belong to a certain space x in space. Okay, so those are functions that go from the time interval 0t to the space x, such that their x norm belongs to LP. Okay, that's the definition. Well, we can analogously define the space of sequences, the LP sequences, the space of LP sequences, which would be the space of sequences in time, but I mean that those will be time levels, such all of them belonging to the space x, all are functions of x, that sequence, such that the equivalent to the LP norm, to the x norm is LP, is that the sequence is LP. So that means that the sum of the time step times the norm of Fn in the space where it corresponds, and if you want, if it's in LP, to the power of p is bounded, and if you want the p root of that, the p root of that is bounded. Okay, so what we are doing in these discrete spaces is replacing the integrals, because LP means the integral. LP, of course, means that could mean that the integral of the norm of f to the power of p is bounded from 0 to t. Okay, or if you want the p norm of that, the p root of that. So that we simply replace time integrals by the sum of the components of the sequence multiplied by delta t. So this is, if you want, a discrete version of the integral. Okay, good. So now we say, in particular, we say that the sequence belongs to L infinity in L2 if the L2 norm is bounded for all components of the sequence. Okay, the sequence in time. We say that. And we say that the sequence is bounded, in particular, in L2, LP-L2, if, that is what is said here, if the discrete integral is bounded. And likewise for when the space of arrival is H1, so that's just a particular case. The only thing is that the H1 norm is denoted with a subscript 1 here, okay? And the -1 norm can be denoted here. So what is the result that we have? The result that we have is this one. For the method that is written here, for this method, it turns out that the solution happens to be bounded in the correct spaces. But be careful, be careful. The end of a step velocity, the velocity that is divergence free, the velocity that is divergence free is only bounded in L infinity in L2. However, the intermediate velocity is what is bounded in L infinity L2 intersection L2 H1. You remember, this is the discrete version of the continuous space where the Navier-Stokes equations are posed that we saw yesterday. Okay, yesterday we saw that the solution belongs to the continuous counterpart of this space. L infinity in time with values in L2, intersection L2 in time with values in H1. Why is that? Why is that we have full control L2, L infinity L2, L2 H1 in the intermediate velocity and not full control but only L infinity control on the fine end of a step velocity? This is called end of a step velocity. Well, it's very easy. If you look at this equation, you can tell me why. You can tell me why. From where will you find the H1 control of the intermediate velocity? From which term will you find the H1 stability of the intermediate velocity? From which of these terms in red? The H1 is the control of the gradient. In the weak form, where does the gradient come from? From which term comes from? From where? Which one? Who wants to point it? Point it. No, here. This one. This term. No, this term no. This one. When you test against the test function, and you integrate by parts, you get the integral of the gradient of V gradient of U tilde, and that's what gives you the control in H1. Okay, that's what gives you control in H1. That term doesn't give you any control. Remember, when you test against U tilde itself, what is the result of that? When you test this term against U tilde, if U tilde were divergence free, that would be 0. If not, that has to be controlled. That is not 0 because this one is not divergence free, but has to be controlled. Okay, has to be bounded in terms of the other terms. Okay, so for U tilde, we can have H1 control, but what about the end of a step velocity? For the end of a step velocity, we don't have any derivative, so we cannot expect anything. We only have the control that comes from this term that is only in L2, right? So we only have L infinity L2 control. So that's the stability result. By the way, the method was introduced by Jorin and Temam in 69, I guess. Both papers were published in 69, but the analysis is later, and the convergence analysis didn't appear until about 10 years later. And that's the convergence analysis. The convergence analysis says that the error in time, you see, that's the approximated velocity, and that's the exact velocity at the end. So this is the error in velocity. This is the error in the end in the intermediate velocity. You see, the intermediate velocity can also be taken as a velocity. I mean, it's not divergence free. The one that is divergence free is this one. This one is not divergence free, but I mean, you could see whether this one approximates the exact or not. And that's the error in the pressure, okay? So it turns out that convergence in the end of a step velocity happens only, of course, only in the space where we have stability, and it's of order delta t. It's a first order scheme. Then convergence in the intermediate velocity holds in a norm that is more interesting numerically because it controls derivatives and is order delta t. So both the end of a step velocity and the intermediate velocity are approximations of order delta t of the exact velocity. And pressure only converges with order delta t 1/2. So it's so that is not a very good scheme because it's only first order, but that's not that bad, you know, because here we have the error. We have two errors, in fact. Which are the two errors we have? The first error is the one that comes from the time differentiation. So we have used backward Euler. No, that's said here. We have used backward Euler, okay? So because we have used backward Euler, we have already a first order error. Also, I mean, an error of order delta t. So that's not that bad. It means that the uncoupling, the splitting, has not increased the order of the error. Okay? So that's not that bad. Good. And that's what I was saying before. that problem requires, so that is the so-called the projection step, requires the solution of the velocity and the pressure in a coupled manner. However, it's very easy to uncouple those two equations just by taking the divergence of the first. If you take the divergence of the first and you know that the divergence of un plus 1 should be 0, you end up with this Poisson equation for the pressure, okay? And that has two advantages. First, that uncouples the calculation of the velocity and the pressure, and that is a consequence that relates this to stabilization. At the discrete level, that modifies when you, that taking the derivative at the continuous level is exact, but taking that at the discrete level is not exactly the same. We will see that at the discrete level modifies the continuity equation, and that introduces diffusion. How can this be explained? This way. Look, what we do is the following. Well, here, the other day I wrote the matrix of the gradient minus d transposed, and then the matrix of the divergence d. Here I have changed the notation. I have written the matrix of the gradient G, and I have written the matrix of the divergence minus G transpose. You can. The fact is that this one is the transpose of this one with the change of sign. That's the important thing. Why the change of sign? Because you integrate by parts. Okay, so that's the problem you have in the projection step. Okay, so if you do that, you have a mass matrix divided by delta t. When you discretize using finite elements, a mass matrix divided by delta t times the nodal unknowns of u minus the nodal unknowns of the intermediate velocity plus a gradient matrix that multiplies p equal to 0. And then you have divergence of u equal to 0. That's what the two equations, the two first equations are those. Okay? And now the second equation, this one, the Poisson equation, has this structure. Delta t times the Laplacian of p, delta t, I have moved delta t to the left hand side, delta t Laplacian of p minus the divergence of u tilde equal to 0. That's what I have written here. Oops, sorry. Minus the divergence of u tilde equal to 0. Okay, that's the expression of the second equation. That's the algebraic. So now let's see. We have at the discrete level we have these two equations. These two equations lead to these two, and this one leads to this one, but they are not exactly the same. Look, what happens if from this equation, we eliminate the end of step velocity? So we know what the end of step velocity is. Okay, we know what the end of step velocity is. And then if we eliminate the end of step velocity and we put it here, we eliminate the intermediate velocity. Sorry about that. We eliminate the intermediate velocity and we put it here. We eliminate the intermediate and we put it here. What we get is this. Instead of getting divergence of u equal to 0, we get divergence of u plus delta t L minus G transpose D minus 1 G equal to 0. And this is very interesting, and in fact that is what motivated the introduction of certain subgrid scales that I will mention in the application subjects. So let's take a careful look at this expression, because that, as I said, motivates the use of what we called orthogonal subgrid scales. Let's take a look at that. So you see the equations I'm solving are, well, divergence of un plus 1 plus delta t. I prefer to write divergence rather than minus G transpose. Times L. L is the matrix of minus the Laplacian, in fact. L minus divergence of m minus 1 gradient of p equal to 0, and then I have exactly I have to put a plus, but this is minus the Laplacian. Anyway, I have to put a plus, but this is minus the Laplacian, in fact. So this L is the matrix of minus the Laplacian. Let's write it this way. L, to distinguish between this one and this one, let's write it this way. L is the matrix of minus of the Laplacian, and the L that appears there is the matrix of minus the Laplacian. This is the Laplacian. So what does that mean? Look at this. We have divergence of m minus 1 gradient minus L0 multiplying by p. What is that? These are two different manners of computing the gradient, the Laplacian, sorry. Two different manners of computing the Laplacian. At the continuous level, this would be exactly 0. This would be exactly 0. The divergence of the gradient is 0. But at the discrete level, it's not 0. It's different. Why? Because at the discrete level, discretizing the Laplacian of the pressure gives L0 of the pressure. Okay? Discretizing the Laplacian of the pressure gives L0 of the pressure. And the Laplacian, you know, that is the divergence of the gradient. The divergence of the gradient. However, discretizing the gradient yields the gradient of the pressure. The gradient of the pressure, if you discretize the gradient. Then, that you have to project it back to the space of velocities so as to be able to take the gradient. So you project it to the space of velocities, and then you take the gradient, the divergence, sorry. You take the divergence. And this happens to be different to the Laplacian of the pressure. And you may say, I don't know, is that true? It's very easy to understand. Very easy to understand. Look, imagine we do that at the using finite differences. Using finite differences. Using finite differences, imagine you have the second derivative of a function u over x twice at a certain node I, using centered finite differences. Centered finite differences means this is node I, this is node I plus 1, this is node I minus 1, and the distance between nodes is h. Okay? Centered finite differences means this is ui plus 1 minus twice ui plus ui minus 1 divided by h squared. That's the approximation to the second derivative. Now assume you approximate the first derivative. The first derivative at I is equal to ui plus 1 minus ui minus 1 divided by 2h. That's the approximation to the first derivative. And now you want to approximate using finite differences the derivative of the first derivative. The derivative with respect to x of the first derivative is equal to 1 over 2h, the first derivative at I plus 1 minus the first derivative at I minus 1. Okay? The first derivative of at I plus 1 minus the first, but that would be equal to 1 over 2h of the first derivative at I plus 1 is ui plus 2 minus ui divided by 2h minus ui minus ui minus 2 divided by 2h. So at the end what you have is 1 over 4h squared times ui plus 2 minus ui plus 2 minus 2i plus ui minus 2. So in fact, you have taken a wider stencil when you discretize using centered differences the derivative of the derivative. Well, that's exactly the same. That's exactly the same. First, one thing is to approximate directly the Laplacian, and the other is to approximate the gradient and then take the divergence. Okay? So it's not mysterious. Well, that is the reason why, well, that's an important reason. We will see why. Yes, in both cases, in all cases.
Take forward difference, then this will be equal.
No, but I am being consistent. I am using, that's exactly what I would get using finite elements, for example. If I use finite elements, I would get that for the approximation of the second order derivatives, and I would get that for the approximation of the first order derivatives. Exactly this. If I use finite elements, I would get exactly this, the same as in finite differences with centered schemes. So what I'm saying is that if I discretize directly the second derivative, or I discretize the derivative of the derivative, I would get different things, in one case with a wider stencil. Okay, that's the only thing I'm saying. Okay, and that introduces a stabilization. What does that introduce a stabilization? There is the final result of this section is that this matrix happens to be positive definite. That can be shown. It can be proved that this matrix is positive definite. And therefore, in fact, you are introducing dissipation, and that allows you to stabilize pressure. Okay, boundary conditions. This is a point of interest in the case of fractional step methods because boundary conditions are always controversial. Why are these controversial? Because for the velocity in this equation, in principle, you cannot prescribe, or in this one, you cannot prescribe all the velocity components. You can prescribe only the normal one. Only that's from the mathematical point of view. If you have a function that has the divergence well defined, you can prescribe the normal component, but not all of it. The space where it belongs is called H dip. We already saw that space, and we will see it later. So the point is that you can prescribe the whole boundary conditions for the intermediate velocities because you have all the derivatives controlled, but you can prescribe only the normal component of the end of step velocity. And the other problem of fractional step methods is that if you look at this equation, and you take the normal component of this equation, you see that the normal component of u on the boundary is going to be equal to the normal component of u tilde on the boundary, right? And if this is equal to it on the boundary, it happens that the normal component of the gradient is 0. That's bad luck, you know. So that means that the derivative of p with respect to the normal is 0. That's a spurious boundary condition that is known to happen in the case of fractional step methods that leads to spurious pressure boundary layers, which, however, do not prevent convergence to be order delta t to the power of 1/2, as we have seen before. So, but that's a problem of fractional step methods. Okay, that's a problem of fractional step methods. Okay, that problem is first order. In fact, once that we know that we have a splitting method, one can design second order methods. So, to design second order methods, we want to solve this equation, the compressible Navier-Stokes equation. So to design second order methods, we have to do, in fact, two things. The first thing is that we have to make sure that the time integration to design a second order method, we have to have the time integration, of course, second order. The time integration should be second order. That's the first point. And the second point is that the splitting, the error that we do when we split the equations, has to be also second order. Okay? The error that we do when we integrate in time and the error that we do when we split the equations has to be second order. Let's think about the splitting error. If I discretize the equations as we have seen before, we have seen that the equations that we have to solve are those. Let's forget about the convective term. And then we have un plus 1 minus u tilde n plus 1 plus the gradient of the pressure equal to 0, n plus 1, and divergence of un plus 1 equal to 0. Okay, so this is the first step and this is the projection step. I haven't put the convective term. Okay, so what happens with the splitting error? Splitting in which sense? This is the error that comes from the fact that I have separated the equations, in fact, from taking here the intermediate velocity. Let's see what happens if we add the two equations. If we add the two equations, we have un plus 1 minus un, because this cancels with this, over delta t, plus or minus nu Laplacian of u tilde n plus 1, plus the gradient of the pressure at n plus 1 equal to f, and divergence equal to 0. So, okay, perfect. You see which is the error, the splitting error? The splitting error is due to the fact that here we have the intermediate velocity, not the end of step 1. Great. And of which order is this splitting error? I mean, this splitting error is u minus u tilde, and if we compute u minus u tilde, we see of which order is u minus u tilde. It's very easy. U minus u tilde is of order delta t times the pressure, so it's order delta t. Is it clear? So u minus u tilde is of order delta t. The error, which is the difference between u and u tilde, is of order delta t, How would we get a second order splitting error? U minus u tilde should be of order what? Delta t squared. How can we get here an error of order delta t squared? What? No, only with that step. In that step, I have to modify that equation. Let me see if you surprise me. How can I obtain from this equation, with a modification of this equation, a splitting error of order delta t squared? What? No. No, because u minus u tilde is going to be always, u minus u tilde is going to be delta v times delta t times something. If you want the error be order delta t squared, that something has to be of which order? Delta t. And how do you manage to modify gradient of pressure, instead of having the gradient of the pressure, having something of order delta t? How do you do that? You are close to the solution. How do I have to add or subtract? Okay, you are almost there. You are almost there. So u n plus 1 minus u tilde n plus 1 is going to be delta t times something, and I want this to be of order delta t. But the gradient of the pressure alone doesn't work, because the gradient of the pressure is order 1. Pardon me? Delta t? No. So I'm saying that is going to be, that will multiply, that has to multiply something that cannot be the gradient of the pressure. Has to be something of order delta t. Has to be something of order delta t. In other words, it has to be gradient of something, and that something has to be of order delta t. Because remember that in the splitting, we have to have the gradient of a certain function phi. So that has to be the gradient of something, but that something has to be of order delta t. If it's not the pressure, what could it be? What? No. It has to be a scalar. It cannot be the velocity. It has to be a scalar, because you have to take the gradient of it. The answer is almost there. You are almost there. Can I add or subtract something to the pressure to make it order delta t? If I put here the pressure at n plus 1, what do I have to put here to have something of order delta t? I don't have an intermediate value of pressure. Not the intermediate. What is the value of pressure I do have? What? You are almost there. What? Who says that? P tilde. Where, have you seen P tilde anywhere? No, I don't have P tilde. It's easier. What do I have? I am integrating in time. It's easier. Come on. What? It's very easy. Come on. Minus Pn. That's it. That's it. Hopefully, if everything works, the pressure at level n plus 1 minus the pressure at the previous time step will be something of order delta t. Isn't that? Yes or not? You see that? Okay, so the point is that to modify that scheme, I have to put here minus the gradient of the pressure at Pn, which is known. But then what happens? If I add these two equations, I will have the gradient of Pn plus 1 minus the gradient of Pn, which is not what I want. What do I have to do to correct and still obtain something that is consistent. Well, at the end, you see, when we added these two equations, we have to get the gradient of the pressure at n plus 1. So I have to add here the gradient of the pressure at n plus 1, so that when we add the two equations, we get exactly this expression. Okay? So that's the modification. With that modification, it happens that the difference between un and un plus 1, if everything works, of course you have to prove that everything works, the difference between un and un plus and u and u tilde will be delta t square, of order delta t square. Therefore, the difference, the splitting error, which is what you see here, the splitting error is because I have here u tilde instead of u, will be of order delta t square. So that's what second order methods do. Second order methods do that. So what we have to do to design a second order scheme is, first of all, we start with a second order time discretization. So that's what it said. We start with a second order time discretization, for example, Crank-Nicolson. This is what they're written here. And once we have a second order time discretization, we do a second order splitting. Well, that's either Crank-Nicolson or the other methods that we saw, ABCN if you want. And then we do a second order splitting, which is this one with gamma equal to 1. The splitting is this one, okay? The splitting is, you keep here the gradient of the pressure at the previous time step, gamma is equal to 1, in principle 0, 1. 0, you have a first order splitting, once you have a second order splitting, okay? And then in the projection step, you subtract the velocity at the previous time step. And the error un minus un plus 1 minus u tilde n plus 1 is of order delta t plus gamma. So if gamma is equal to 1, gamma is equal 1 or 0. If gamma is equal to 1, you get a second order error, okay? And that can be proved rigorously. So this is the scheme you finally get. That's the scheme you finally get. You solve first for an intermediate velocity with the gradient of the pressure at the previous time step. Then you compute the Laplacian of the pressure, taking the divergence of the equation. You compute Pm plus 1, that is known. And then you obtain the end of step velocity, un plus 1. It turns out that the scheme is convergent, and converges to second order in velocities and also in intermediate velocities, okay? In velocity and intermediate velocities. And also first order in pressure. This is surprising because even though the fractional step schemes of first order weren't designed in the very late 70s, 69 was the paper published, as I said, second order schemes were proposed in the beginning of the 80s, and that proof is due to Shen, who proved that in 85, I think. So quite late, okay, quite late. Good. There are also discussed the splitting method, but I will skip that. Okay. And then all what we have said at the continuous levels can be done algebraically. That is a repetition of what I have said before. Algebraically, we start from the monolithic discretization, and then now that we know, I mean, the origin was this fractional, this splitting, Helmholtz decomposition, so on. But at the end, when we know what we want, you can do it algebraically, and it's easier. Okay, easier and more powerful. But that's another topic. So we start from the discretization of the Navier-Stokes equation, for example, using the theta method or the trapezoidal rule, wherever. So you have the time derivative, mass matrix, the derivative or incremental quotient of the nodal unknowns, convective and diffusive term, pressure gradient, right-hand side, and divergence of u. Okay. So that's those are the equations. So what we do now is we split the equations. We split, and in principle we do that splitting purely algebraic, which is exact. You know. That the original equations can be written in this way. That's exact. What have I done? Here I have replaced the incremental quotient by u hat I plus 1 minus u, but then I subtract here u hat in the second equation. So if you add these two equations, you see that this term cancels with this, and likewise this one cancels with this. Therefore, if you sum these two equations, you get exactly the first equation. So it's exact. So it's just a game, okay? Just a manipulation. So that has no advantage. Why it has no advantage at all? Contrary, I mean, it's disadvantageous. It has no advantage because now we have one more unknown, and the system is still coupled because here we have u that is exact, the same u as we have here, the same u as we have. So it's a coupled problem, with many degrees of freedom. However, what's the point? The point is that the difference between u hat and u is of order delta t times the order between Pn plus 1 minus Pn, which should be delta t, so it's delta t squared. So what we can do is here, you know, the critical point is here, replace the viscous and convective term evaluated with the end of step velocity, replace that with the evaluation with intermediate velocity. So that's the key point. Why? Because now we are able, just by doing that, we are able to solve directly this equation, which is now uncoupled from u. You see? It's a simple game. So that's useful. Then we solve for the Poisson equation for the pressure. This is the discrete part. And then we solve for the end of step velocity. Okay, so it's exactly the same. Then at the algebraic level, we can do the previous approximation. We can replace that discrete Laplacian, that would be the discrete Laplacian, the divergence m-1 gradient. We could replace it by the standard one, which is the discretization of the Laplacian. And therefore, we would have to solve this equation. Exactly, that's exactly what I said before. So we have done that at the discrete level, but once we have arrived to this matrix, we could approximate that matrix by the standard Laplacian, which is an approximation to the same operator, but a different approximation. Okay. Okay, and the approximation is of order delta t squared. Well, as I said before, here there are many terms, but at the end, it turns out that when you do that approximation, this approximation, so you compute the continuous Laplacian instead of the discrete one, what you get is that you modify the continuity equation by this term. Okay. So the error, apart from the splitting error that you do, apart from the splitting error, you have that blue term. The splitting error, as I said before, is of order delta t 1 plus gamma. Gamma is equal to 1 is order delta t squared. We have that term, and that is a beautiful term because that introduces stability. And let me make one remark. Very often, you will see in the literature that fractional step schemes can be used without satisfying the if sub condition. Okay, you will see that very often. Why is that? Because when you take gamma equal to 0, you have a stabilizing term that gives you control in the pressure. As we have said before, that's what I mentioned here, the stabilization effect comes from this term, this matrix big, that happens to be positive semi-definite. So that gives you control on the pressure, this term. However, first point, first bad thing, that control is not given by something that depends on a space. The instability of the pressure is in a space. However, the amount of stabilization depends on the time step. So if you have a time step that is very small, you may lose this control. That's the first thing. And the second thing is that if you use an incremental fractional step scheme, so a fractional step scheme of second order, that control is only not for the pressure, but for the increment of the pressure, which is extremely weak. Therefore, when you reach the steady state, when Pn is equal to Pn plus 1, that is lost. So it oscillates when you reach the steady state. So never use fractional step schemes without any additional stabilization, either in superstable elements or stabilization, as we have seen before. Okay. Okay, so that's the overview, the quick overview that I wanted to give about fractional step schemes. As you see, these points are related to stabilization, pressure stabilization in particular. Now we can understand that. And now I will go to three topics. Let me recall what I said yesterday. We will go to 4 topics. One today, now, and a little bit of this afternoon, and then this afternoon, and the 2 sessions tomorrow. So once again, one is about turbulence. It's the one that I will talk about now, which is large eddy simulation, variational multiscale in the context of large eddy simulation for Navier-Stokes. Then I will talk about Darcy's problem, then magnetohydrodynamics, and waves. So this is the plan, okay? This is the plan, but I may change it if you wish. So these 3 topics, what I have presented so far, I have said several times that I have tried to be, let's say, general, to make an overview of the literature and to be, let's say, as objective as possible. You know, you can never be objective, but as objective as possible. Now, what comes are 3 talks. That I have given along the years. Those correspond to plenary sessions, and therefore they are more or less general. They are overviews. They are not very technical, so they are all plenary sessions and therefore more or less general. and on 3 topics that are related to the course, of course, and using stabilized methods of VMS type related to the course. If today, for example, you think that there might be another topic that could interest you, and I have enough material to present it, I would do that, okay, for tomorrow. So that's the plan. The plan is now, and a little bit of this afternoon, variational multiscale in large eddy simulation. Then Darcy's problem, magnetohydrodynamics tomorrow morning, and waves will be the last topic. That's the plan, okay? So let's go to the first one, which will take us today and a little bit of this now and a little bit of this afternoon. So that's, as I said, a plenary talk that I give already 4 years ago. Those are part of my colleagues, and it's about a purely numerical approach to model turbulence in incompressible flow. So it is a plenary talk, so it's not very technical. So I hope you will follow that. The first part, in fact, is just what I have explained about Navier-Stokes in the chapter about Navier-Stokes. Okay. So the first part is very general to introduce the audience to the topic. So the problem, the Navier-Stokes problem, that's what we saw yesterday morning. Transition to turbulence and large eddy simulation. So part of it was already said yesterday. I will repeat it now. Part of it is new. Then numerical instabilities and variational multiscale. Again, part of it is already said. Part of it is new. And then this is new, okay? Modeling conditions and energy balance equations, features of our variational multiscale model, some examples, and the summary. So part of what I will say now is what I said yesterday when I introduced the Navier-Stokes problem, okay? So let's introduce the problem, and that is, as you see, is known. That is what I already said yesterday. So the Navier-Stokes equations, the incompressible Navier-Stokes equations, okay? So we have to find the velocity u and the pressure p solution of this system with initial conditions, simple initial conditions in this case, and simple boundary conditions and initial conditions. A summary of what I said yesterday: the solution exists in the functional spaces where the problem is well defined. Remember, here I haven't written the spaces, but we know that these are L infinity in L2 and L2 in H1. However, uniqueness is an open problem. That's what I mentioned yesterday. Existence is proved, but uniqueness is not. For a smooth data, it means that if F and the initial condition are smooth, the solution exists and is unique in spaces more regular than those where the problem is well defined, but the problem is that only for finite time intervals, only for short times. That's the problem. Global existence of regular solutions is also an open problem. So we have these two problems: either uniqueness of weak solutions or global existence of regular solutions. Regular, you know what regular means. Remember, it's very technical, but I think it's a nice problem. Regular means that instead of being L infinity L2 intersection L2 H1, the solution has to be perhaps in L infinity L4, only a little bit more, or L2 H2 instead of H1. If you have either of these two conditions, you have a regular solution, and the solution is unique. And that's the one of the millennium problems. Right? I didn't say that. Maybe these were called millennium problems. Did I say that? Okay, I said that. Those were posed by Hilbert. Okay, so those are the equations. What is transition to turbulence and large eddy simulation? We talked yesterday about what is called transition to turbulence. I will repeat it here, and now we will define what is large eddy simulation. So, as I said yesterday, the parameter that plays the main role in the Navier-Stokes equation is the Reynolds number, which is defined here: a characteristic velocity times a characteristic length divided by the viscosity. And disregarding the uniqueness issue, so assuming that the solution is unique, the flow behavior when we increase the Reynolds number and as time tends to infinity is the one that I mentioned yesterday. So we have these iterations. First, the solution converges to a steady state. then it converges to a periodic state if the Reynolds number is increased. Of course, there is not a particular Reynolds number at which this happens. That depends on the problem, obviously. Okay. Then we have a case in which the Fourier transform is, has a discrete spectrum, is quasi-periodic, and then in the final stage we have a chaotic flow that is what is called turbulence in fluid mechanics, which can be defined in several ways. I think the most interesting one is the one that I mentioned yesterday, that the Fourier transform in time of the function has a continuous spectrum. All frequencies are alive. Okay, that's the most, let's say, graphic way to understand the problem. Another way to see the problem is that the solutions tend to a strange attractor. What is a strange attractor? This is also general culture. You know, what is the attractor? The attractor is very intuitive. The attractor is the manifold to which the solution tends. It does not necessarily get there. It just tends when time tends to infinity. Okay, so when time tends to infinity, the solution moves in a manifold. Okay, the solution moves in a manifold, around a manifold. So that manifold can be a classical one with integer dimension. So it can move in a manifold of an integer dimension, 3, 4, 10,000, whatever. But it could happen that the dimension of the attractor is not an integer. Is a fractal dimension which is not integer. That is what could happen. So what is a fractal dimension? Is in essence you have to count. You have to take every point, take neighborhoods of every point, estimate the dimension of the neighborhood, and then take the limit when the neighborhood gets closer and closer to the point. So it's very technical, and there is the way to compute fractal dimensions is not unique. There are several fractal dimensions. Maybe the most classical one is the so-called Hausdorff dimension, but there are others. Okay, there are others. So what is a strange attractor? That strange word. A strange attractor is an attractor that has a fractal dimension which is not integer. Okay, that is well. This is a picture of. This is a picture of how solutions look like. So you have oscillations after obstacles. You may have, this is a jet entering a flow region. So you have that complicated flow pattern. There are lots of vortices everywhere. So not only big vortices, but lots of vortices everywhere. When you see these bands, there are also vortices in these bands. So all frequencies are alive. Maybe not everywhere, but in the whole of the domain, all frequencies are alive. This is, for example, this is a picture taken from the outer space. Those are the Canary Islands. This is one of the Canary Islands. That's a real picture, and those are clouds. Okay, those are clouds, and you see the vortices that emanate from that island. You know, that island is just a perturbation in the flow, and that produces that behavior. For example, in the case of ordinary differential equations, not in the case of partial differential equations, but in the case of ordinary differential equations, you can plot the attractor. For example, if the solution at the end evolves in a manifold like that one, that would be a non-strange attractor that would have dimension 2. This is a torus. Okay. However, there are strange attractors, as you probably know. There are strange attractors. Maybe the most well, there are several well-known strange attractors. Let's wait. I think that goes. Yes, that goes out. Okay. In that you cannot define the dimension in an integer way. Okay. So as also I said yesterday, the steps from 1 to 4 are Hopf bifurcations, and in the case 4 we have the energy spectrum that has 3 clearly defined regions: the region corresponding to the large scales, the region corresponding to the very small scales, and the region corresponding to the inertial range. That's exactly the same picture that we had yesterday. Okay. That was new. That is not new. Okay. What is large eddy simulation? To understand what large eddy simulation is, we have to understand very well this picture. So to understand what large eddy simulation is, it is crucial to understand this picture. Crucial. So the objective of large eddy simulation is the following. I said that here we have a range for large scales, so small wave numbers means large scales, in which the solution is driven by the external forces and the boundary condition and the initial condition and the data in general. I should have said maybe the data. Okay. So we don't know what it happens. We don't know. That could be, I have plotted that because that's what people usually plot, but it could have any shape. Then we have a region of very small scales, so very large wave numbers, in which viscous effects dominate, and then the solution, the energy rapidly decays up to zero. Okay, up to zero. The solution rapidly decays. Here is where viscosity dominates. And then we have a region in which there is a linear decay of energy in terms of the wave number, which is called the inertial range. So what is the objective of the so-called large eddy simulation models? Those are models. So that corresponds to very, very, very small scales that we will not be able to reproduce numerically, so forget about that. By the way, I didn't say that the dimension of the attractor, maybe I should have said that, the dimension of the attractor can be estimated as the Reynolds number to the power of 9/4, 9 over 4. That's an estimate for the dimension of the attractor from the physical point of view. From the mathematical point of view, there are estimates for the dimension of the attractor that are much worse. The best one, I think, is, I don't know if it's 15 over 4 or something like that. There are worse estimates. There is a group between Israel and US trying to work on that. There is a mathematician called Titi that does the, I don't know if you heard of him, Edris Titi, who tries to estimate the dimension of the spectrum of the attractor. Well, the point is that large scales, small scales are very small, and you can forget about reproducing them. That would amount not to billions, but to billions of elements. So only in general, only in very simple cases, you are able, in very simple situations, you are able to capture these regions. So very large wave numbers means very small length scales. Okay. So what is the objective of a real calculation? The objective of a real calculation is, of course, to obtain that behavior here, more or less, and to obtain part of the inertial range. Why? Because as soon as we know that we have entered the inertial range, we know that we have a turbulent flow, a fully turbulent flow when we enter this. And then, of course, we will not capture everything up to the end. What we expect is that our dissipation, the numerical dissipation, will start playing a role before the dissipative range. Okay? But at least we know that we have entered the turbulence behavior. So that's what we want. So LES model, what is called a large eddy simulation model, aims at computing the flow up to the inertial range, and then, of course, this spectrum will decay somewhere. You understand? So methods that try to reproduce all the spectrum, exactly, are called direct numerical simulation method, DNS. But they are only useful for very simple geometries, boxes, no, only boxes, essentially, okay? Using, you just let the flow run over a plate, and that's the most complicated you can afford, using DNS, direct numerical simulation. So LES, large eddy simulation, means that we want to capture that range. Okay. So what is LES? As I said before, the objective is to set an equation for the large flow scales. Large flow meaning that the wave number is smaller than the so-called Kolmogorov wave number. That limit is the Kolmogorov wave number. So the objective is to set an equation for the large flow scales. What is the idea of LES, not of what we claim, but of LES? The idea is to filter the Navier-Stokes equations, so to filter the high fluctuating modes, and to model terms that depend on the non-filtered variable. So what does that mean? It means that we want to reproduce the solution up to a certain point in the inertial range, but we have to model what is behind. What does it mean to model what is behind? It means to give a closed form expression for what is behind and capture the effect of what is left on the main scales. Okay? very similar to what we said about variational multiscale. That's the objective. Well, how is filtering done? Filtering of the Navier-Stokes equation is done as filtering in any case. Filtering is essentially convolution with a smooth function. Filtering is when you have a signal, when you have an oscillating signal and you want to filter it, what you do is you convolute it with a smooth function, with a function that has less scales. That function is called kernel, as you know. Okay. And what is the nice thing? The very nice thing, when you filter, that convolution has the property that the regularity of the filtered solution is not the regularity of the initial solution, but the regularity of the filter. So this is amazing, because you can take a function that is very rough, you filter it, and you can obtain a function almost as smooth as you want. So this is a surprising property. And then if we assume that the filter commutes with the derivatives, what we can do is we can take the filter of the Navier-Stokes equations, which are written here. We can take the filter of the Navier-Stokes equations, we filter this term, we filter this one, and this one. But what's the problem? We may assume that the filter commutes with the derivatives, but the problem is going to be these nonlinear terms, because when we take the filter, so here we will have the time derivative of the filtered velocity, but here we will have the filter of the product. And the filter of the product is not the product of the filters. You know, all the problem relies on the fact that the filter of the product is not the product of the filters. So at the end, when we take the filter of these equations, here we have the filtered velocity, the filtered pressure, the filtered velocity, and so on, the filtered right-hand side, whatever it is. But we have a problem here. We have the filtered product, and what we want is the product of the filter. Because of course, our unknown is going to be the filtered velocity. That's what our unknown is going to be. So that's the problem. And how do we deal with this problem? Well, that's the real difficulty. So we will have, that's what we will have when we filter. So everything will be filtered. But here I have written the product of the filter, and that's not what we have. So we have to subtract the appropriate thing, which is what I have added. I have added the product of the filter, but I have added the product of the filter, so I subtracted, but what we originally had was the filter of the product. You see? By the way, as you notice, what I have used the following expression for the convective term. Instead, it's the expression that I introduced yesterday, which is the divergence of the dyadic product of u times u. Okay? So I have used the divergence of the dyadic product of u times u. This is the convective term. So we want to take the filter of this. The filter, I write an overbar for the filter, and that is equal to, what I said is that the divergence of the u bar dot u bar is equal to the divergence of the filter, which is what I really have. What I really have, it's something nonsense. That is what I really have is the divergence of u bar cross u bar minus the divergence of u bar cross u bar plus the divergence of u cross u. Okay, so it's a stupidity. But what I have done is I have left this on the left hand side, and I have moved that to the right hand side. So it's as stupid as this. Okay, that's why I have this divergence of t, where t is this tensor that is called the subscale tensor. Okay, t is called the subscale tensor, and it's the difference between the product, the filter of the product of the velocities minus the product of the filtered velocities. Okay, and then what you have to do, since there is no way to know how it behaves, then what you have to do is to model t. And in applied mathematics, modeling means that you just propose equations. You propose equations, not equations that come from fundamental principles, but you just propose equations. So which are the equations that are proposed? Example is Smagorinsky's model. So I will not, this is not a course on large simulation, so I will not explain how it comes, but one example of closure, this is called a closure model. One example is Smagorinsky's model, where you say that that tensor happens to behave as a certain constant times a length, all this squared. So this is a characteristic length. This is a characteristic length delta. In principle, it should be, I haven't said here, but in principle, it should be the diameter of the filter. So the diameter is the diameter of the region where the filter is not zero. Excuse me, the kernel is not zero. Okay, that's the diameter of the filter. Well, that should be a length, and that's the so-called Frobenius norm of the symmetrical part of the gradient of the filtered velocity. Anyway, this is, all that looks very strange. How is that? The arguments to arrive to this expression are very strange. I mean, to me, they are very strange. I mean, and what's the point? The point is that there, when you do that, you are done, because then you have a problem that involves only the filtered quantities, involves only u bar and p bar, because on the right-hand side, you have replaced t by something that depends only on u bar. So you are done. Okay, you are done. You can code that. You can code this model and obtain results, and that more or less works. More or less works. Comments. I mean, I am not, let's say, objective in that topic. Okay, I assume I am not objective. So there will be some comments here that are personal opinions, but. One fact, this is one fact. LES models pretend to be previous to any numerical approximation. We haven't talked about any numerical approximation yet. That's just filtering. But in practice, what happens is that there is a relationship between that filter length and the mesh size, h. So that was, I mean, we haven't talked about numerics yet. However, in practice, people take delta equal to h, the element size. Mysterious. Then the other point is that one can obtain an exact equation for u bar, the filtered velocity. And the filtered velocity satisfies that equation in terms of the non-filtered velocity. Okay? So that you can obtain that equation for the filtered velocity. That is exact. That can be shown. It's not difficult. That was due to Germano. However, but that makes the problem for u bar, for the filtered velocity, as complex as the model for u. What does that mean? It means that even though the solution is much smoother, the solution u bar is much smoother than the solution, the fluctuating solution u, so u bar is much smoother than u, it can be shown that the dimension of the attractor is the same for u bar as for u. So in principle, you haven't gained anything. Even though the solution looks simpler, the dimension of the space where it lives in the long term, when time tends to infinity, is the same as the dimension of the original solution. So, you know, back to the original problem. So this is a real conceptual problem. And the other thing is that Smagorinsky's model, after all this reasoning, is similar to a model that Ladyshenskaya introduced, not with the length scale equal to the mesh size, but just to a length scale. She proposed that model in the 50s already, okay, just by intuition. And by the way, she showed that if you do that, the solution exists and is unique. You know, that's something Ladyshenskaya proved. Ladyshenskaya proved. Of course, Ladyshenskaya was aware that there was not uniqueness of solutions. I mean, the uniqueness in R3 was proved by Leray in the early 20s, but Ladyshenskaya was working from the 40s to the 70s, more or less, or maybe a little less. And she was perfectly aware that there was this uniqueness problem, but she was able to prove uniqueness if to the Navier-Stokes equations you add this type of viscosity term. So this stress, this type of viscosity term. Okay, good. So that's transition and large eddy simulation, basic concepts. Let's talk about the numerical instabilities and the variational multiscale formulation. This is already known for you, I guess, I hope. So, although the presentation is different, I have introduced here a different representation. Suppose that we have the simplest backward time integration scheme applied to the Navier-Stokes equation with Coriolis forces, just for fun. To the Coriolis, do the Navier-Stokes equations with Coriolis forces. So this is only first order in time. I did that just to make things simpler. It's easier to work with time discrete equations. Okay, so we have the discretization of the time derivative, the convective term, the viscous term, the pressure gradient, and I have included the Coriolis force just to highlight that we may have problems. Okay. Okay. Now we can obtain what is called an energy estimate. An energy estimate very easily. An energy can be obtained easily in this way. How do you get that? You multiply this equation by n plus 1. You multiply this equation by n plus 1, and you integrate over the domain. You obtain what is called an energy estimate. And what do you see? As we saw yesterday and the other days, when you multiply by un plus 1 and you integrate, since the divergence of un plus 1 is 0, this term disappears. When we multiply by un plus 1, this term, it also disappears, even without integration, because the scalar product of un plus 1 by omega cross un plus 1 is exactly 0. Okay, this is the the vector product, and this vector is perpendicular to un plus 1, and therefore, when you take the scalar product with un plus 1, it's exactly 0. So these two terms are 0 when you multiply by un plus 1 and you integrate. This term is what leads to viscosity times gradient gradient. We know it very well. And that term also disappears because when we integrate by parts, we know that the divergence of u is 0, so that term disappears. And what about that one? Here we have the norm of un plus 1 is squared, and here you have un plus 1 times un. Okay, you have un plus 1 times un. Okay, you can use, I will not do the details, but to deal with this term, un plus 1 dot un, you can use Schwarz inequality. It is smaller or equal 1 over 2 un plus 1 squared plus 1/2 of un squared. Okay, with a minus sign. So with a minus sign, this is greater or equal. With a minus sign. Okay, with a minus sign, this is greater or equal. And then this term, cancels with the first one, with un plus 1 squared. Okay, so you have un plus 1 squared minus this, which is greater or equal to, smaller or equal, because you have this term, 1/2 of un plus 1 squared minus 1/2 of un squared. Okay, this is that un squared, and that cancels with this one. And now you use what is called a telescopic sum, because you sum for all n, and then each one will cancel. For example, you have 1/2 of un squared minus, here you would have also un minus 1/2 of un minus 1 squared. Then you would have 1/2 of un minus 1 squared minus 1/2 of un minus 2 squared, and so on. And so when you add up all the terms, those cancel. You see, this cancels with this cancels with this, and so on. And at the end, you are left with the very last one. Okay, do you understand the process? You are left with the very last one. This is called telescope sum. Well, at the end, the estimate you get is this one. The estimate that you finally get is that estimate, you see? So, first comment, you see that you have un minus 1. This is the end of a step, the final velocity, the final time velocity. And then on the right-hand side, I've put the initial condition, because that is what will be left when you make all this sum. You see, you will have the last one minus the first one. So I move the first one to the right-hand side. This 2 is due to this 1/2 that is multiplying here. And you see that we have control on the viscous term, but neither control on the convective term nor control on the Coriolis force. So those are bad news. And then we have a constant that multiplies the sum of the forcing terms multiplied by delta t. Okay. If we assume that the right-hand side is bounded, which is a strong assumption, if we assume that the right-hand side is bounded, then we have the following. We have that the L infinity L2 norm of u is bounded, so the maximum for all n, because that I can do that sum for any n I want, for any number of time steps. So the maximum is also going to be bounded, and the sum, that sum is also bounded. So that means that I have control in L infinity L2, and the viscosity to the power of 1/2 times the velocities belong to L2H1. And that's the problem, because, you know, first, that is nice. That I always have this. I always have this. But this is bad, because when the viscosity is very small, this is not meaningful. That does give me much information. That's one thing. That this is small, so it doesn't give me information. And the other thing is that the convective term and the Coriolis force is completely out of control. We have no control on it, okay? Well, the same estimates can be found using a classical Galerkin method. If we use a Galerkin method, we obtain exactly the same thing, the same stability estimates. So what are the stability pitfalls of the Galerkin method? That's what we have seen in yesterday, essentially. We have to satisfy the IMSUB condition to control the pressure. So the previous equations have no pressure estimate. For the continuous problem, one has to rely on the IMSUB condition for the velocity and the pressure. And for the discrete problem, that has to be explicitly imposed. And that, as we have seen, imposes stringent requirements on the velocity pressure approximation, in the sense that we have to, not any pair of velocity pressure spaces satisfies that, and we have to be very careful. That estimate U belongs to L infinity L2 is very strong in time. L infinity is very good. You know, L infinity is the best, the finest norm you can hope. I mean, you cannot expect more than bounding everything pointwise. You know, but L2 is very weak in time, weak in space. Why L2 is weak in space? Because knowing that something is bounded, okay, it's a good information. But if we know that it is bounded, everything can happen below the bound, you know. So it can be perfectly oscillating. So having an L2 estimate is not good at all. So it's not very nice. I mean, in general, in numerical analysis, we have 3 types of estimate. Well, maybe 4 if you include L1. L2, which is very weak, L infinity, which is perfect, and H1, which is something in between, but usually reasonably good. What does it mean? In L infinity, we control pointwise the solution, point by point. In L infinity, in H1, we control the derivative. In a weak sense, but in L2 only, but the derivative. And in L2, we only control the L2 norm, which is not much. There is one even weaker that you need to use, for example, in plasticity or compressible flows, which is L1. L1 is almost nothing. You know, you control only the integral. That is the weakest estimate. And then the comment that I made before, that estimate, so that estimate is strong in time but weak in space, and that estimate is meaningful only meaningful is if the viscosity is large. And usually it is useless for small realistic values of the viscosity, okay? So we have more. What happens? We don't have, as I said before, we don't have any control on the convective term if it dominates the viscous one. This is measured by the cell Reynolds number. So control on the convective term is measured by the cell Reynolds number, so which is just the Reynolds number, but replacing the length scale by the element size, okay? That's what controls. We have seen that in the context of the convection diffusion equation. Do you remember which is the analogous number for the convection diffusion equation? Which is the analogous, the number that measures the ratio between convection and diffusion, but for Navier-Stokes, for Peclet number. So that's the Peclet number. In the Navier-Stokes equation, the number that matters is the cell Reynolds number. For large Reynolds number, we know that instabilities may appear, and they appear, apart from complex physics in Navier-Stokes. Okay, we know the problem of convection-dominated force. And there is also this problem that there is no control on the Coriolis term if it dominates the viscous one. And that dominance, the dominance of the Coriolis term over viscosity is measured by so-called Ekman number. The Ekman number is the rotation speed times a length size squared. In the case of the local Ekman number is the size of the elements, and then the viscosity in the numerator. Okay, this is dimensionless. There is a dimensionless number because this is length square over time, and this is also length square over time because the units of the speed of rotation are 1 over time. When the Ekman number is very, very small, then you may have numerical instabilities, and they really appear. Okay. What is the variational multiscale? In fact, two-scale formulation that we use to solve these problems is exactly what I have presented these days. The idea is to decompose our space into a velocity space and a finite element space and the complement, and the same for the pressure, a pressure space and the complement, and split the unknown into the finite element solution and the rest, the complement, and the pressure into the finite element component and the rest. Okay. And as I mentioned these days, but I have only explained the simplest approach, different models can be obtained depending on the way the subscales for velocity and pressure are approximated. These are the subgrid scale components of the solution in that variational two-scale formulations. In the literature, you can find also sometimes three-scale splittings, but those are very unusual. So, within this framework, and with some additional assumptions, as we have seen in previously, some classical stabilization methods can be justified. For example, it's very similar to GLS or very similar to SUPG. Okay. Another comment is the key point is the splitting of the velocity, which is split into the finite element part and the rest. And contrary to LES formulations, now the finite element space is well defined. So the filtering is not required if we accept that decomposition. And from the subscales, we only need its effect or their effect on the finite element solution, and the same for the pressure subscale. We only need the effect of the subscales on the large scales, okay, on the finite element scales. When we approximate the space of subscales, we have seen one approximation, but we will see another one now. That is the one that we favor. The result is a finite dimensional space, of course. I mean, at the end, V prime is approximated by a finite dimensional space. Therefore, in fact, choosing V prime implies choosing a projection, implicitly defines a projection from the continuous space to the finite element space. We will see that. It is also possible to design that decomposition in not only in a space, because those are the spaces, this is the space in space. It is also possible to design that decomposition in time, and that was abandoned, that has been abandoned, I would say, but that was the so-called nonlinear Galerkin method developed by Marian and Temam and others, Temam's group, in the early 90s. And in fact, the point is that considering the idea of splitting U, the unknown, into a larger scale, that in our case is the finite element space, a larger scale, something that is computable, plus something else, appears in many physical and mathematical theories, in turbulence, in homogenization, in acoustics, in many cases. Okay, that is a very natural idea. So you just split the solution into what you can capture and what you cannot. That is simple. Now the question is variational multiscale in this sense, in the sense of that splitting, a large eddy simulation model? Well, in variational multiscale there is no filtering, but there is a closed form expression for the subscales. In variational multiscale there is no ambiguity on what is a subgrid scale. It is clear what a subgrid scale is. We define UH as a certain projection of the continuous solution, and that's the subgrid scale. It is what is remaining, okay? It is what is remaining. Most likely, I will explain that later, variational multiscale, sorry about that, that should be S, variational multiscale is a large eddy simulation model, but I mean, the point is, and we will further talk about this, when you have variational multiscale, is it necessary to consider an LES model? We will further talk about that. In other words, turbulence modeling is a physical or a numerical issue. This is a little bit, looks like philosophical, but it's like it is. I mean, it is not still clear what turbulence modeling is. I mean, when you say, suppose I am a turbulence modeler, whatever it means, you know. I'm a person whose job is to design turbulence models. So is that person a numerical analyst or is that person a physicist? So is turbulence modeling a physical or a numerical issue? Not clear, you know, not clear. Something in between, something blurry, I would say. And the answer depends on the way turbulence modeling requirements are met that we will see. Okay. And in fact, there are requirements in turbulence modeling, and they can be really stated. Which are the requirements that turbulence modeling has? And we will talk about that this afternoon. Okay. So this afternoon we will talk about the requirements of turbulence modeling and the features of our variational multiscale model satisfying these requirements. Okay. So I will see you this afternoon.